Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Let V be the vector 4, -3, 5, and U the vector 4, A, 1. Find the value of A so that the projection of U onto V is the vector 6/5, -9/10, and 3/2. All right. So the question is, which A makes all of this work? And we might as well say, okay, do we know how to compute this? Yes. All right, there's a formula for that. So if I want to find the projection of the vector U onto the vector V, I usually like to put parentheses. So I'm taking U onto V. This is U dot V over V dot V times V. And in other words, it's really a multiple of V. Which makes sense because we're projecting onto V. We want to be pointing in the direction of V. So that's our goal. Is like we have our formula. What makes this work? Well, let's think about what's true for a minute here. We know that this right here, this is a scalar, and a scalar is just a fancy way of saying a number. All right, great. And this is our vector V. And so we say, hey, we need to have that this output is a multiple of that. So let's actually figure out what that output needs to be. What multiple is going on here? So let's see. We have 6/5, -9/10, and 3/2. And there's some scalar that if I multiply V by that number gets this. And so we're like, well, let's first get rid of fractions. I look at the denominators, 5, 10, and 2. I say, okay, well, the least common denominator would be 1/10. So let's start there, and hopefully that'll help. So if I pull out 1/10, that would leave me with a 12, a -9, and 15, right? Because, here I got the full 10th. Here, it's like, well, to pull out a 1/10, I need to multiply the top by 2, right? This is 12/10. Here I multiply by 5, 15/10. And I say, okay, well, that's a lot closer. And then I say, I see now. Pull out a factor of 3, right? Because 12 divided by 3 is 4. -9 divided by 3 is -3. 15 divided by 3 is 5. So we say, okay, so this is 3/10 of 4, -3, 5. Perfect. Perfect. All right, now this helps a lot. Because what does this tell us? Well, it tells us now that this number, this 3/10 here, this has to be the U dot V over V dot V. All right, so let's update. We now have that 3/10 is equal to U dot V over V dot V. And now we're ready to do our dot products. We have our U and V up here, so we say, okay, U dot V. We take 4 times 4, 16. Minus 3 times A, minus 3A. 5 times 1, 5. All right, divide that by V dot V. Okay, so V dot V. So 4 times 4, 16. Minus 3 times minus 3, plus 9, right? The negative goes away when you multiply it by itself. 5 times 5, 25. All right. And we're almost done. And let's just clean this up. Okay, 16 plus 5 makes 21. Then we're going to subtract 3a. And here, 16 plus 9 That's 25. Plus 25 makes 50. Okay, 50. All right, so we have now 3 over 10 is equal to 21 minus 3a over 50. And, all right, now we could do a couple of things here. One thing is, that has a factor of 3. We could pull it out. That has a factor of 10. We could pull it out and cancel. But here, I'll go ahead and say, let's cross multiply. Because, well, I'm always nervous about fractions. You know, once or twice I had a bad experience with fractions, and I said, okay, I'm going to be super careful. And one of the ways to be careful is to say, get rid of them. So cross multiply. And we have what? 3 times 50, 150, equals 10 times 21 to 10 minus 10 times 3a, minus 30a. We're almost there. Move some things around. So move some terms around. This becomes 30a equals 210 minus 150, and that would be 60. Okay, now 30a equals 60, or we could say, aha, a equals 60 over 30, also known as 2. And there we go. The answer was 2. All right, great. No problems. And, well, I mean, one problem, but, okay. What was the idea? We had the formula. And so we said, all right, we write down u dot v over v dot v times v. We say, all right, well, let's figure out what the coefficient u dot v over v dot v needs to be. That was where we got the 3/10. And then once we had that, we said, okay, we have this coefficient of 3/10. We have this series of dot products, and we just work it out. And life is good. Life is wonderful. All right, let's keep going. Find 2 integer values of c. Wow, first off, we know that there's 2 of them, and we know that they're integers. That's so cool. Okay, such that 2 minus c, 2c squared plus 3, negative 5, is perpendicular to c plus 1, 1, 5. All right, now, here's a little note. Perpendicular, sometimes we'll use the word orthogonal. And what does it mean? Well, really what we're thinking is, we're thinking that right angles. That's what we're thinking. We like things being perpendicular. A lot of cool things come with perpendicularness. So you're like, okay, well, how do we know? And so the key here is we say, oh, this really means that the dot products are 0. Because what's going on? If you think of the dot product, it's, you know, the magnitude of u, magnitude of v, cosine theta. The perpendicularness says the angle, the theta, is a right angle. Cosine of a right angle is 0. So we say, all right, now we know what we're looking for. We want to take the dot products, set it equal to 0, solve. Well, all right, let's take our dot product. So we're going to set 0 equal to the 2 minus c, comma, 2c squared plus 3, comma, negative 5, dot c plus 1, 1, 5. Okay, so take the product of the first terms, 2 minus c times c plus 1. Add the product of the second terms. And, well, that's a 1. That makes it very easy to take the product. 2c squared plus 3 times 1. And add the product of the last terms, negative 5 and 5. Okay, now notice where are we at now? This is 0. This is a polynomial. So the problem reduces to find roots of a polynomial. Algebra! Algebra. Algebra. Yeah, right? It's algebra. Oh my gosh. Well, we love that algebra, right? Great times. Okay, so let's go ahead. We'll do some foiling here. We get 2c plus 2 minus c squared minus c. good times. Now we'll distribute the 1 in, which is not very hard to do. It's just you just multiply by 1. 2c squared plus 3 and minus 25. Okay, now we enter into sort of our hunter-gatherer type phase, right? We're hunting for our powers of c. We're going to gather them together. So for c squared, there's a 2c squared and a minus c squared. So, okay, c squared. For the c's, there's a 2c and there's a minus c. And, well, that's it. So that's a plus c. Then finally we have our constants, a plus 2 and a plus 3 and a minus 25. So that's 2 plus 3 is 5, minus 25, minus 20. All right, good. And we see that every term has been accounted for. And now we have to factor. But we know it will factor. Right? I didn't say let's use the quadratic formula. I said let's factor. How do we know it's going to factor? How do we know it's going to factor nicely? That word, integer. Integer tells us it's going to factor nicely. Okay, so we see there's going to be a c, and then there's going to be a c, and we need two things that multiply together to give negative 20 and add to give 1, right? There's really a secret coefficient of 1 times c. Okay, so think of how you can multiply to get 20, and it's not too long till you get like, oh, 4 and 5. And you're like, yeah, 4 and 5. And now the question is which one gets added, which one gets subtracted? Well, we should add 5, subtract 4. Because 5 minus 4 is 1. Now let's check. C squared, good. Minus 4c plus 5c is a single c, and then minus 20. All right, now follow the equalities. That all equals 0. So that tells us what? Well, it tells us that we have 2 answers, which is good because we were told there are 2. And the answers are going to be c equals negative 5 and c equals 4. And that's it. We're done. Yay! Woohoo! Woo, 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 woo. All right. Well, no big surprises. Just here, the key is to understand what's meant by perpendicular and use that to our advantage to find the answer. All right. Good job. Let's keep going. Find the area of the triangle having vertices 3, 2, 1, 4, 5, 5, and 2, 3, 5. Simplify your answer. All right. Now, we see a couple of things. One thing that we see is area. Okay, so this is going to be something that relates to area. And another key thing that we see is triangle. All right, good. So we have area and we have triangle. Now, let's talk about this for a moment. How do we find the area of a triangle? What information stores area? Does anything cross your mind? Okay, so this is about cross product. And here's the idea. If you take 2 vectors, and let's say these are our 2 vectors, and you can say, well, look, put them together, and then you can actually sort of move them around, and you can form what's called a parallelogram. And the area of a parallelogram is the magnitude of the cross products. Okay, so if this is our u and v, you're like, okay, well, that's all great, and we can talk about area of parallelograms, but we're not after areas of parallelograms. We're after areas of triangles. So how do we get that? Well, now it's a great because what can you do? Well, you can do the following. You say, okay, our area, you can say same sort of picture initially, but now instead of making a parallelogram, make a triangle. Now, how does the area of the triangle relate to the area of the parallelogram? Well, the answer is it's half of it. You're like, what? It's half? Well, okay, we can handle that. So that means that this area is going to be 1/2 of the magnitude of u cross v. And we're like, okay, great. Now we know our plan. We're going to take u cross v, magnitude 1/2. Life is good. Now, you're probably thinking, okay, but wait, don't I have 3 vectors? No, currently you have 0 vectors. What do you have? These are all points. We don't have any vectors. So we say, so we should make some vectors. So that's where we start the computation for this problem. So we're here in 3-dimensional space. So we'll just draw 3-dimensional space. And we're not going to stress about getting it just right. The thing is, we don't need to get it just right. We just need to get some intuition going. So we have the point 3, 2, 1. We have the point 4, 5, 5. And over here we have the point 2, 3, 5. Those will be our 3 points. And we're forming a triangle in 3-dimensional space. So we have our triangle here. I'll do it with a dashed line for just a second. And that's what we're after. What's the area here? Now, what do? We have a plan. We need vectors. And so, how do we make vectors? Well, we go between points. And we have 3 points, which means we actually have 6 possible vectors, right? Because there's a vector from here to there, but we can also go back, and you can do that for each side. And so the key here is just to make sure you have a good logical set. And the way I like to do it is I say pick a vertex, any vertex. And let's suppose we pick this as our vertex. And now make the vector from that vertex to the other vertices. And so let's see how we change. So if I go 2 to 3, that's a change of 1. 3 to 2 is a change of -1. And 5 to 1 is a change of -4. So 1, -1, -4. All right. Now here, we went 2 to 4. That's a change of +2. 3 to 5, that's a change of +2. And 5 to 5 is a change of 0. 2 to 0. Now, you might be wondering, how do I know I picked the right corner? There's not a wrong choice. Now, you'll get slightly different vectors to work with. Any set that you work with will produce the same final answer. So don't like overthink it. And say, okay, so now that we have our corners all identified, our vectors all picked out, you can just, it's not a bad idea to double check, because everything from here will just go automatically, and you want to make sure the numbers are working like they should. All right, so we're going to take 1, -1, -4, cross 2, 2, 0. Well, that is going to be the same as finding the 3 by 3 determinant I, J, K. 1, -1, -4, 2, 2, 0. And we start doing our diagonals. So we have 2 sets of diagonals, right? We have the diagonals going down and diagonals going up. That's what I like to think of them as. So we have I times -1 times 0. Okay, that's 0I. J times -4 times 2. Well, that's -8J. K times 1 times 2. That's 2K. All right, that's one set of diagonals. And now we have another set of diagonals. One's going uphill. 2 times -1 times K. It's -2K. But we're going uphill, so we're going to subtract. So, right, subtract -2K. 2 times -4 times I. That's -8I. But again, going uphill, subtract. So subtract negative 8i, and then 0 times 1 times j. That's 0j. We're going to subtract it. So subtract 0j. And we put these all together. What do we have? Well, 0i minus minus 8i is going to become a plus 8. Minus 8 minus 0, it's a minus 8. And then a 2 minus minus 2, it's 2 plus 2, that makes 4. And I say, there we go. 8 minus 8, 4. Now, what can we do? Well, one thing we should do now is check ourselves. As the great philosophers have said, you should check yourself before you wreck yourself, right? And so we say, okay, well, how do we check ourselves? The cross product will always be perpendicular to what we started with. So we do a quick dot product check. Okay, 8 minus 16. Add those together, you get 0. 16 minus 16, 0. Add them up, 0. Okay, so that's the dot product check, right? Take the dot product of the output with the two inputs separately. If the dot products are both 0, that's usually a good sign. And almost always that's a sign you did it right. If the dot product is not 0, that's a sign you definitely did it wrong. So it doesn't hurt to check. We want all our points. So it's sort of like it's an insurance policy. And like, hey, we want to make sure that we're going to get all the points we can. All right, so we're almost done. We found the cross product. And now we need to take the magnitude times a half. Well, here we go. So the area of the triangle is going to be 1/2 the magnitude of 8, negative 8, and 4. Well, let's take advantage of one thing we have. Notice 8, negative 8, 4 all have a common factor of 4. So we can do the following. See, this is 1/2 of the magnitude of 4 times the vector 2, negative 2, 1. And now, the nice thing is we can bring the 4 out of the magnitude. Because if I'm scaling the vector by something, I know how that affects the size of the vector. And you might say, well, wait, you're talking about length. I thought you were talking about area. It's one of these cool things where it turns out the length is an area. But not in that the literal length is a little area. Okay, I'm getting too philosophical here. But, okay, maybe I should avoid that road. Okay, but we can pull this 4 out. So, okay, so we have 1/2 times 4 times the magnitude of 2, negative 2, 1. So if you see common factors in vectors, you can pull those out, and that can help simplify computations. So what do we have? Well, we really have 2 times the square root of 2 squared, 4, negative 2 squared, 4, and 1. Well, you add that up, you get 9, and the square root of 9 is a nice number. So we end up with 2 times 3, or 6. So the area of our triangle that we were asked to find is 6. Woohoo! Nice, nice. All right. I will say that one of the most common mistakes people make on problems like this, the cross product usually is not too bad once you get the hang of it. It's to say, oh, wait a second, these are not vectors. These are points. So sometimes people are like, oh, I'll take the cross product of these two vectors. No, those aren't vectors. They're points. And if you take the cross product of points, it doesn't make any sense at all. And so be careful. Make sure that when you're dealing with cross products, you're dealing with vectors and not points. So just watch out, pay attention. We're going to be great. We're going to have a wonderful time. All right, let's keep going. Find a unit vector perpendicular to both 3, 2, negative 2 and 1, 2, negative 1. All right, so there's a couple of pieces going on here. This word unit says that the vector needs to have length 1. Remember that unit corresponds to 1. All right. Now, that's actually sort of a last thing we worry about. what's the first thing we need to worry about is, well, we need to make something that's perpendicular to both. And so we have two vectors. We want to have something perpendicular to both. And this helps sort of like, oh, if you want to make perpendicular, how do you do it? Now, test perpendicular, dot product. Make perpendicular, cross product. So there's a nice basic fact. U cross V, this cross product is perpendicular to U, and U cross V is perpendicular to V. So if I have two vectors, and I want to make something that's perpendicular to both simultaneously, then I want to do a cross product. So we have a plan. What's our plan? We're going to start with our two vectors. We're going to form a cross product. That'll satisfy the perpendicular to both. So that means we've got the right direction in some sense. Now the last thing we need to do is we need to make it the right length. And that's where the scaling comes. So we're going to scale at the end. So the unit will making it a unit vector. That'll be the last thing we do. All right, so here we go. So we're going to take our 3, 2, negative 2, cross that, 1, 2, negative 1. We set up our matrix, I, J, K, 3, 2, negative 2, 1, 2, negative 1. All right, time for us to go and do our diagonals. So we have our down diagonals and our up diagonals. Okay, so we have I times 2 times negative 1, which is minus 2I. J times minus 2 times 1, minus 2J. K times 3 times 2. That's 6K. All right, those are going our downs. Now we need to do the ups. Okay, so 1 times 2 times K, that's 2K, but we need to subtract. Okay, so subtract 2K. 2 times minus 2 times I, because we do our wraparound, minus 4I, but we're going to subtract that. And minus 1 times 3 times J. That's minus 3J, but again, we're subtracting. All right, so we put all these together. What do we have? Well, we have minus 2I, minus minus 4, so that's really plus 4, so that gives a total of 2I. Minus 2J, minus minus makes plus, and so that'll be plus J, and 6K minus 2K is plus 4K, or in component notation 2, 1, 4. All right, now, quick check. Is this perpendicular to both, right? We can check. We test perpendicular. We test orthogonal. Dot product. 6 and 2, subtract 8, makes 0. 2 and 2, subtract 4, makes 0. So this vector here, this is good in that insofar as it's perpendicular to both. Okay, now it's not the final answer. What is the final answer? Well, we haven't made it a unit vector. And is this vector length 1? Hopeless, right? Look at that, 4. That says it's got to be bigger than 1. So now, after we found the right direction, we make it the right length. Okay, so let's make it into a unit vector. So how do we do that? Well, we're going to figure out the current length. So we say, what's the magnitude of the vector 2, 1, 4? Well, it's going to be the square root of 2 squared, which is 4, 1 squared, which is 1, and 4 squared, which is 16, which is the square root of, well, 4 plus 1 is 5 plus 16, 21. And the square root of 21, also known as the square root of 21. Okay, so not everything will work out nicely. Okay, so that's the current length of the vector. So now we scale down. So we say, okay, take 1 over the square root of 21 times the vector 2, 1, 4. And so that is the answer. And there we go. We're done. Now, I'm going to pause and say, I said that is the answer. Actually, that is an answer. Is there another answer? That's correct. Can you think of another vector that would give us the same conditions? That had length 1, and it was perpendicular to both those directions. There is one. There's one other one, exactly one other one. And what is that vector? Well, the vector is, we could have gone the negative of this vector. So minus 1 over square root of 21, 2, 1, 4. So there's actually 2 of them. Now, where does this one come from? Well, if you think about it, it's just saying instead of going this way, go that way, right? It's just like go the exact opposite direction. Now, if you're the exact opposite direction, you're still perpendicular to both that you started with, and you have the same length. And on a side note, you would get the negative if you swap the order that you take the cross product. Because if you take u cross v, that's different from v cross u. They differ by a sign. And so these are both correct answers. So it is possible that if you're studying with a friend and you both do a problem that involves cross products, that you compare your answers like, wait a second, I got the negative of what you got. That's fine. That can happen. So don't panic. That's a totally fine thing. But okay, which one's right? They're both right. They'd both get full credit. And it doesn't say find all of them. It just says find a unit vector, right? So that's good. It didn't say find all of the unit vectors or find the unit vector, because it turns out there's multiple correct answers. All right, there we go. Wonderful. We're doing great. Let's keep going. Suppose that u1 and u2 are orthogonal unit vectors, c and d non-zero scalars. All right, so we have our assumptions. Now there's a lot of stuff built into here. Unit means length 1, and orthogonal means that if you look at the two vectors, they form a right angle. And so here, the orthogonal has some information. So to be precise, the orthogonal condition tells us that u1 dot u2 equals 0, right? That's how you tell if two things are orthogonal. The other condition, this unit condition, tells us what? Well, it tells us their magnitudes are 1. We can phrase that in terms of dot product. It says u1 dot u1 equals 1, and u2 dot u2 equals 1. So that's the first sentence that we have these relationships. All right, now we're told if v is cu1 plus du2, find u1 dot v and explain your answer. All right, well, here we go. So we're going to take u1 dot v. So that's u1 dot, and replace v by what it is. cu1 plus du2. Now, what can we do? Well, dot product has some nice properties. One nice property it has is you can distribute. Okay, so we're going to distribute here. And so this becomes what? Well, this becomes c u1 dot u1 plus d u1 dot u2. Okay, so this is by distributive rule. Since they asked us to explain, we'll go ahead and make some notes here so they know what's going on. And then we say, we know some things. u1 dot u1, this is 1, since u1 is a unit vector. And u1 dot u2, we already marked it here. This is 0, since u1 is perpendicular to u2. So this becomes what? It becomes c times 1 plus d times 0, which is c. Oh, say, can you see? All right, and so that's the answer. It's C. Wow, that was pretty easy. And where's the explanation? Well, we can distribute, and then we have properties that came from these words orthogonal and unit. The orthogonality told us this second part was 0. The unit told us this first part was 1. So here's the explanation that they asked for. You know, because if it asks for an explanation, we should do more than just try to say, oh, this is C. It's like, okay, here's the process, and here's why the steps were justified. And that's the problem. Wow, that didn't take long. I will say that this sort of hints at fun things that might show up depending upon the future roads you take. If you end up in a course about linear algebra, this kind of thing will happen from time to time. It's a beautiful idea. But for us, we're done. Let's keep moving right along. Let theta be the angle between vectors u and v. Given that the magnitude of u equals 2, the magnitude of v equals 3, and 3u plus 2v dotted with 2u minus v equals 11, find cosine theta. All right. Now, I will say we know that the dot product is going to be involved, but we can see because there's a dot product. But there's another big clue, the fact that it says cosine theta. If you see cosine theta, you're like, wait a second, cosine theta, I know about that. That shows up in the dot product. Yeah, it does, right? So we note that we have this nice property, u dot v is the magnitude of u, magnitude of v, cosine theta. So we suspect that dot products will be involved. And what do we do? Well, let's work through it. And we'll start with our nice equation here. So we say, well, we know that 11 is equal to 3u plus 2v dotted with 2u minus v. Now, there's a distribution property, distributive rule, and the dot product follows the distributive rule. Now, what does that allow us to do? It allows us to FOIL. Okay, so now let's FOIL. Okay, so here we go. We take the first in the terms, so the first and the first, okay, so that's going to be 3 and 2 make 6, u dot u, and then we're going to take the outer, 3 minus 1, that makes minus 3, u dot v, and then we have our inner, 2 and 2, well that makes 4, so plus 4 v dot u, and our last 2 and minus 1, that makes a minus 2, and we have v dot v. Now, v dot u and u dot v are the same thing. We'll put those together. So I'll just write this as 6, u dot u, minus 3 plus 4 makes a total of 1, and so plus u dot v, and then we have minus 2 v dot v. And what can we do? Well, we can say these individual terms have interpretations. And so we say, all right, let's go through and think about these. U dot u, if I take a vector dot itself, what comes out? It's the magnitude of u squared. U dot v, well, we mentioned this before, that's the magnitude of u, magnitude of v cosine theta. And v dot v is the magnitude of v squared. Now, we know some of these things. We know the magnitude of u, and we know the magnitude of v. So let's put those in. All right, so what do we have? We have 6. Magnitude of u squared, that's 2 squared, makes 4. So 6 times 4 plus magnitude of u is 2. Magnitude of v is 3. And we have cosine theta. Minus 2. And we have magnitude of v squared. Okay, so that's times 3 squared, which is 9. Okay, so we have 24 plus 6 cosine theta minus 18. All right. Right, 24 and 18. Now 24 subtract 18, that's known as 6. So this becomes, we're near the bottom, we'll have to move over. 6 plus 6 cosine theta. All right. Now, we're almost done. So what have we shown? We've shown that 11 is equal to 6 plus 6 cosine theta. So what do? Well, we subtract 6, and 11 subtract 6 makes 5 is equal to 6 cosine theta. And now we divide, and we get cosine theta equals 5 over 6. And there we go. We're done. Now, one small check, it's not a perfect check, is this number between -1 and +1. If it's not, we definitely made a mistake. And the good news is, it's between -1 and +1. Now, that doesn't mean we're right, but at least it doesn't mean that we're completely wrong, right? So that's the idea. And so, no real big surprises. It's just a matter of understanding that we can FOIL, and then using the information that a dot product with itself gives us magnitude squared, and a dot product is magnitude u, magnitude v, cosine theta. Put it in, work it out. Life is good. That's what it's about. All right, let's keep going on. Let v be the vector 3, -2, 6. Find all unit vectors u such that the vector u looks like 0, a, b, and cosine of theta is 2/7, where theta is the angle between u and v. All right, now there's a couple of clues here of things we're going to do. In fact, there's 2 clues. One big clue is it told us not theta, but cosine theta. Now, anytime we see a cosine theta, we're like, dot product, because that's part of the expression for cosine theta. So we're like, okay, so we recall that u dot v, that's our magnitude of u, magnitude of v, cosine theta. All right, so that's going to come into play. Now, there's a second thing that's going to come into play, and that is that we need to make sure we have a unit vector. Okay, so that tells us that our vector, u, will have length 1. And let's start. Okay, so we know magnitude of u equals 1. We're going to keep that in mind. Okay, so we have magnitude of u equals 1. So we have these nice 2 facts. And let's start with this one. All right, so we have u dot v. So we're going to take our 0, a, b dot 3 minus 2, 6. And that's going to be the magnitude of u, magnitude of 0, a, b, magnitude of v, 3 minus 2, 6, and the cosine of theta. And let's go ahead and clean this up. There's a couple of things that are going to simplify pretty quickly. Cosine theta we know. That's 2/7. Magnitude of 0ab we know. It's 1. Why is it 1? Because of a unit. It's a unit vector. All right, so that's going to make things pretty clean. And, well, this we have to do some computation. This would be the square root of, and we take 3 squared, 9, minus 2 squared, 4, and 6 squared, 36. And 36 plus 4 is 40, plus 9, this is the square root of 49. also known as 7. Now notice we have 1 times 7 times 2 sevenths, which says this whole side here is going to become 2. Okay, so that's this portion, the right-hand side. Now the left-hand side. Now the left-hand side is a dot product. So we have 0 times 3 is 0, minus 2 times a, that's minus 2a, and b times 6 is plus 6b. So minus 2a plus 6b equals 2. Well, everything here has a factor of 2. And we say, okay, so that's minus a plus 3b equals 1. Now, we're like, cool. But hold on a second. That's one equation, 2 unknowns. Something's not right. Because we're after, if we have to solve for 2 unknowns, we should have like 2 equations. We feel like there's not enough information. But have we used all of our information? Well, you could say, yeah, we used that it was a unit vector. We used that cosine theta was 2/7. Didn't we use it all? Well, couldn't we use it even more? Now, this is the part that's like, what? Right? It's going to be like, what? Because, okay, what else do we have? Well, let's go back to the unit. What does that tell us? Well, one thing it tells us is we get the following fact. We also have that u dot u equals 1, right? Because this is the magnitude of u squared. And, well, 1 squared is 1. So what is u dot u? So that becomes 0 squared plus a squared plus b squared equals 1. Now we're like, 2 equations. 2 equations, 2 unknowns. We're in a much better setting. We can solve. We have hope. All right, well, from here, what do you want to do? When you have 2 equations, 2 unknowns, the goal is 1 equation, 1 unknown. Now, because you see here I have squares and here I don't, we're not going to be able to do some fancy cancellation, which is one of our favorite things to do. So instead of fancy cancellation, we'll do some substitution. And since we have just an a here, that probably is the easiest way to substitute. So we can say, look, a, if we just swap, we get a is equal to 3b minus 1. Okay, so we're going to move it over to here. And this says 3b minus 1 quantity squared plus b squared equals 1. Well, okay. Well, what does that tell us? We square this, that's 9b squared minus 6b plus 1 plus b squared equals 1. And as if it was planned, because I think it was, the ones cancel. Whew! Good. That'll make things a little bit nicer, right? Because what do we have? We really have 10b squared minus 6b equals 0. And now we have to solve. And how do we factor this? Well, we can factor by just sort of pulling out some terms. So let's pull out a 10b. So we have 10b times, well, here it'll be, and b minus what? Well, 6 over 10, also known as 3/5 equals 0. So what does that tell us? Well, now we say, look, there's 2 possibilities. All right, the 0 had to come from somewhere. So it says we have either b equals 0 or we have b equals 3/5. So what's the answer? What are our choices for A and B? Well, let's start with b equals 0. If b equals 0, then A equals 3 times 0 minus 1, which is minus 1. So we end up with the pair A equals minus 1, B equals 0. Okay, so that's one possibility. And by the way, this is not our answer. Even though I box it, we have to be careful. We want to write it in vector form, so we end up with the vector 0, minus 1, 0. That's the real one. So that's the one that we should. We'll highlight it. Extra highlighting. All right. The other possibility here is what? B equals 3/5. Okay. What is A? Well, we're going to take 3 times 3/5, which is 9/5, subtract 1, which gives us 4/5. Okay, so there's our A and B. And so what's our vector? It'll be 0, comma, A, 4/5, B, 3/5. And there's our second vector. All right, so there we go. 0, minus 1, 0, or 0, 4/5, 3/5. And that's the process. All right, so this one's a little bit subtle because you have to use the magnitude of u equals 1 in two different ways. One way is to say, hey, this term goes away. And the other way is to say, oh, that gives you another equation. And in your two equations, two unknowns. But then once you have it, it all works out brilliantly. It's an interesting thing, trying to figure out how to make it work. And initially, it kind of feels hopeless. It's like cosine theta equals 2/7. Like, what? Is this even going to be nice? And then it is. Isn't that cool? All right. Well, let's think about this for a moment. Enjoy the good times. And now let's keep on moving along. A triangle in space has vertices at 540, AAA, and 744, where A is an unknown constant. Determine all values of A such that the triangle UVW has area 6. All right, so we have our 3 points. All right. And what are they? Well, okay, we have 540, and I'm not trying to be precise in any way. We have AAA, and we have 744. All right, so those are our 3 points, and there's this triangle in space. Okay, and what do we want? Well, we want to say, let's pick our value for A, and maybe there's more than one. It says determine all of them. Maybe there's infinitely many, who knows? But we want to pick A so that the area of this triangle is 6. Say, okay, well, we can do this. How do you find areas of triangles? Well, it relates back to the cross product. So we say, okay, so the area of a triangle, and well, really, if you start with the area of a parallelogram, that's the magnitude of U cross V. So the area of a triangle is half of the magnitude of U cross V. Now be careful, they used U and V here. Those are not vectors. Those are points. And so we can't just be like, oh, well, we have our vectors, we're good to go. No. Don't do that. Be careful. Be careful. All right, so what do we do? Well, the first thing is, let's introduce some vectors. Pick a vertex. Doesn't matter which vertex you pick. I'll go ahead and pick this vertex. And I'm going to form these vectors here. And will I regret this choice later? Not really. In some sense, some may have some slightly easier computations, but they will all produce the same answer. So don't stress too much about it. If you see something nice, use it. And if you don't, just go for it, right? you'll get the right answer any vertex. So let's talk about the vectors involved. All right, so I need to go from 540 to 744. So 5 up to 7 means I went up by 2. 4 to 4 says there was no change. And then 0 to 4 says I went up by 4. So that's the vector 2, 0, 4. All right, that's good to know. Actually, it's a pretty convenient vector, 2, 0, 4. Okay, what about this one? Well, you have a bunch of A's, right? So what do you have? Well, you started at 5, ended at A, so it's A minus 5. And then it went from 4 to A minus 4. It went from 0 to A, so that's A minus 0, so that's A. So we have our two vectors. Now we can take the cross product. And we're like, all right, cross product. Yeah, that's right. That's the spirit. Yeah. All right. So here we go. Let's, so we're going to take our vector 2, 0, 4 cross A minus 5, A minus 4, A. Okay, so this is, we write down I, J, K, 2, 0, 4. Again, don't worry about which one comes first. It will all work out in the end. So this is one of those things where you have options, so don't always fret about, am I making the right choice? There's lots of right choices. And there are wrong choices, but the key thing is there's lots of right choices. So don't stress too much. A minus 4A. All right, so we're going to do our diagonals. And, okay, so here we go. I times 0 times A. Well, that's 0I. J times 4 times A minus 5. So that's going to be plus, well, I'm going to go ahead and write this as 4A minus 20J. And K times 2 times A minus 4. And I'm going to go ahead and write this as 2A minus 8K. All right, so those are one set of diagonals, but I have to do the other set of diagonals too. And, all right, so going the other way. A minus 5 times 0 times K. That's 0K. We'll go ahead and subtract that. A minus 4 times 4I. So we're going to subtract 4A minus 16I. Right, 4A minus 16 subtracted. And then we have A times 2 times J. That's 2A times J. And we're going to subtract 2A times J. Okay, giving us our vector, we have minus 4A plus 16. Okay, that's the first slot. And here, 4A subtract 2A would be 2A. And then we have minus 20. And then our last slot is 2A minus 8. And, all right, well, it doesn't hurt to see if we can at least do a check. You can check with 204. 2 times minus 4A plus 16 is minus 8A and plus 32. 0, and 4 times 2A minus 8, that's 8A minus 32. So at least we're perpendicular to 204, so that's a good sign. It is also true that if you were to go through and multiply here and combine, you'd get 0, but that seems like work. But there we go. There's our cross product. Now, I will say there's one more thing I'm going to do with this, and that is to say, is there anything common? Because we're about to take a magnitude, and if you can pull out common terms, that will simplify the computation. Everything's even. So I'm going to think of this as 2, pull out a scaling factor. Then we have minus 2A plus 8, A minus 10, and A minus 4, right? So I took every term, I divide by 2. Minus 2A plus 8, A minus 10, A minus 4. All right, So we've now found the cross product. So we are getting closer. So we know we have area 6. So we get the following. 6, the area of the triangle, which is 1/2, times the magnitude of this vector, the 2, minus 2a plus 8, a minus 10, a minus 4. And some good news, what do you see? The 2's cancel. Woohoo! Nice. All right. Now, some bad news. We're going to have to do a magnitude which involves a square root. But what can we do? We can square both sides. Okay, so if we square both sides, we get that 36 is going to be the magnitude of minus 2a plus 8, a minus 10, a minus 4 squared. And that is a little bit easier to digest because the magnitude squared is what? Well, that's going to be minus 2a plus 8 quantity squared plus a minus 10 quantity squared plus a minus 4 quantity squared. Okay. Yes. We're going to be able to do a little bit of algebra. Algebra. I'm getting nervous, but we do the algebra and hope we get a nice answer, right? Okay. Let's believe. Let's believe that our teachers love us and they gave us something that will work out. All right, so here we go. We're going to square. So minus 2a squared, that's 4a squared. Then we have minus 2a times 8. That's minus 16a. We have to double that because we're doing our squaring. Minus 32a. And then 8 squared makes 64. The next term. A squared. Then we have our cross terms. Minus 20a. Right? It's 2 times the first times the last. And then plus 100. And this is plus a squared. And then middle term, double, right, 2 times first times the last, so that's minus 8a and plus 16. All right, now let's move the 36 across. So we're going to get that 0, and let's do our gathering, our hunter-gathering phase. So we've got 4a squared and a squared. And a squared, 6a squared. We have minus 32a, minus 20a, minus 8a. All right, so that's minus 32, minus 8, that's minus 40, minus 20, that's minus 60a. Okay, interesting. Now, we have 64. Plus 100, that's 164. Plus 16, that is 180. Yes? 64 plus 100 plus 16, 180. But don't forget, we moved the 36 across, so you have to take 180, subtract 36, which is, altogether now, 144. Right! Yes! 144. Okay, and I understand your skepticism, but it's true. It's true. It is 144. Okay, good. Plus 144. Now, 6, 60, and 144. They all have a factor of 6 in common. So this becomes 6a squared minus 10a, and 144 divided by 6 is a number. It's 64, right? Is it? No, it's not 64. It's 24. Yes, it's 24. Yeah. Double check, right? Okay. Whew. All right. This feels a lot more doable. So we've reduced down to saying, what are the roots of the quadratic a squared minus 10a plus 24? Well, does this factor? And if we've lived a good, clean algebra life, and our teachers love us, and hopefully both those statements are true, it will factor. So I need two things that multiply together to give a positive 24, but when added, give a negative 10. Turns out you can do a minus 4 and a minus 6. Nice! All right, so with that in mind, we say, okay, that leads to two solutions, namely a equals 4 or a equals 6. And there we go. So those are all the values of a, so that this triangle UVW will have an area of 6. So either a equals 4 or a equals 6. Woo! Wow! What a fun problem! What a fun problem. Now, on a side note, I will say this variation of the problem is a bit more technical and challenging than the variation that you're probably looking at as you're trying to work it out. But the process, that's the important thing. The process is all here. You can do this. And I know sometimes when you look at these expressions, you're like, wow! But you can do it. Don't panic. Just work through it methodically. What do you know? Okay, I need to take a cross product. Carefully work through it. Keep track of everything. You're going to be great. You're going to do wonderful things. All right, let's get going. Find the area of the parallelogram defined by the vectors u and v, given that the absolute value of the box product of uv and 3u cross 4v is 108. That is, u cross v dot 3u cross 4v is 108. And you're like, what? But this is going to be not as bad as it looks. Okay, so first off, we're going to forgive our problem writers. These should have been a bold U and a bold V, but that's okay. We love our problem writers. Now, area of parallelogram. That's a clue. We say, all right, how do you find the area of this parallelogram? Well, you take the magnitude of U cross V. So our goal is the following. So what's our goal? Find magnitude of U cross V. And if we do that, then we win. We're done. We've successfully solved the problem. Now we say, well, what do we have? Well, we have that magnitude of U cross V, and we're like, that's nice, dot 3U cross 4V is 108. But we're going to take advantage of a few properties. So we note that this 3U cross 4V is a lot like U cross V. There's just this extra 3-ness and this extra 4-ness. And here's the great thing. Those are scaling factors. So if you scale a piece, then you scale the answer. So what does that tell us? Well, this part right here, we can pull the scaling factor out. So this becomes 12 times U cross V. And you say, well, wait a second. That's a scaling factor. That's involved in the dot product. We can pull that out. So we say, oh, this inside, we can really think of as 12 times U cross V dot U cross V. So we're just pulling the scaling factor out. And you say, well, wait a second. That's the magnitude. And then you have a 12 involved. You can pull that out. So that says that this left-hand side, you can pull the scaling factors all the way out. So we have 12 times the magnitude of U cross V dot U cross V. And then at this point you say, well, whoa, hold on. If I take a vector, which U cross V is a vector, dot with itself, what are we finding? We're saying, well, hey, that says that this part right here, this is going to become, we still have the 12, and then we have the magnitude of U cross V squared. because if I take a dot product of a vector which itself, I find the magnitude squared. Now, technically, it's the absolute value of the magnitude squared, but the absolute value of a positive number is what it is. So we say, aha, that's cool. What does that give us? Well, lo and behold, it says the following. So 12 times the magnitude of u cross v squared equals 108. So the key here is essentially to say, oh, the 4 and the 3 come out, and then what's left is a magnitude squared. And not just any magnitude squared, the magnitude of what we're after. So now we say, well, let's divide by 12. Magnitude of u cross v squared. 108 divided by 12 is 9. And now take the square root. Magnitude of u cross v, square root of 9 is 3. And we say, well, wait. That's what we were after, right? The magnitude of u cross v is the area of the parallelogram. So this is the area of the parallelogram. That's a long word, formed by u and v, which was the thing that we were asked to find. And we're done. So it looks initially scary, but then once you realize, oh, this is testing on can we pull out constants, you're like, great, life is wonderful. Life is wonderful. And let's keep moving along. Find a unit vector perpendicular to the plane PQR, determined by the points 5, 1, negative 3, 7, 4, 1, and 6, 2, 1. Now, what is this telling us? Well, we're in three-dimensional space, and we have 3 points. So we say, okay, we draw our three-dimensional space, and we mark our points. We don't have to stress too much about being accurate. We're just building up intuition. 5, 1, negative 3, 7, 4, 1, and let's say 6, 2, 1 is over here. So, all right, so these are our 3 points. Now, these 3 points are all part of a plane. Now, we haven't technically defined plane yet, but here is the idea. A plane is a flat thing. It's like a sheet of paper, but you can rotate it, pivot it, move it around. Okay, so the nice thing is if I specify 3 points in space, I have a plane. And so a plane is not like an airplane, that's something else. But okay, so we have this flat thing in space. And you say, all right, so here's our flat thing in space. And let's say this is our plane that contains these 3 points. Well, we want to find something that's perpendicular to the plane. And we say, okay, well, when we want to find something perpendicular, it says we want to make perpendicular. How does one make perpendicular? So, because we're after a vector which is perpendicular, anytime you're asked, make a perpendicular vector, you should ask yourself the question, can I use a cross product? Cross product makes perpendicular. And we say, well, okay, we could make a cross product if we could find things that were in the plane. So if I find things in the plane and take the cross product, then I have to be perpendicular to those things, so it must be perpendicular to the plane. And that's the key idea. So pick a point, any point, doesn't matter. I'm going to pick this 5, 1, negative 3. Now, why? Well, because it was the first point. The other thing that has going for it is I like the fact that it's the smallest first entry. I always like the first entries to be positive if I can. All right, so I'm going to take these 2 vectors. And what are those 2 vectors? Well, so I'm going to go from 5, 1, negative 3 to 7, 4, 1. That would be the vector 5 to 7, up by 2, 1 to 4, up 3, minus 3 to 1, up 4. Okay, so 2, 3, 4. All right, doesn't hurt to double check. 2, up 3, up 4. Then I'm going to take the second vector. 5 goes to 6, that's up by 1. 1 goes to 2, that's up by 1. Minus 3 goes up to 1, that's up by 4. 1, 1, 4. And again, doesn't hurt to double check, because as long as these vectors are right, everything else after this is going to be pretty much automatic. And now we're forming the cross product. All right, so here we go. We write down, we have our matrix, I, J, K, 2, 3, 4, 1, 1, 4. And we're going to do a bunch of diagonals, and let's see what's going to happen here. So going downhill, we have I times 3 times 4, 12I. J times 4 times 1, 4J. K times 2 times 1, 2K. All right, now we need to go in the other direction. We need to go, I like to call it uphill. 1 times 3 times K, that's 3K, but we're going uphill, so we subtract it. 1 times 4 times I, that's 4I, subtract it. 4 times 2 times J, that's 8J, but we subtract it. And so what do we have? Well, we now gather we have 12I minus 4I, which means that in our first slot, we're going to have 12 minus 4, which is 8. And then in our second slot, we'll have 4 minus 8, which is negative 4. And our last slot, 2 minus 3, is negative 1. Okay, now let's check. Dot product, 16 minus 12 minus 4, 0. 8 minus 4 minus 4, 0. So we're definitely perpendicular to both things we started with. So we're definitely perpendicular to this vector and that vector, which means that the vector we just found is going to be perpendicular both simultaneously. We have to be coming out of the plane, perpendicular to the plane. And so we're like, we're done! But we're not, because we missed something. What have we missed? There's one other thing we need to do. Unit vector. It's not just enough to be a vector that's perpendicular. We need to be a unit vector. So we say, all right, no worries, no harms, no fouls. All right, so this is perpendicular. It has right direction, but the wrong length. So how do we fix it? Well, we just need to make the length the right thing. So we say, okay, great. We take the magnitude of the vector 8, negative 4, negative 1. And if we do that, we get the square root of 8 squared, 64, negative 4 squared, 16, and negative 1 squared is 1. 64 plus 16 is 80, plus 1 makes square root of 81. And that's a nice number they gave us. That's 9. So the current length is 9. We want the length to be 1. So our answer is we scale. So we're going to take 1/9 times 8, negative 4, negative 1. Now you could move the 1/9 in. I would probably leave it out. And that's the answer. Or technically that's a answer, because it says find a unit vector, not the unit vector, a unit vector. Could there be another one? Yes. In fact, there's exactly one other one. Do you know what it is? Flip the sign. Just reverse it. Or we could have gone negative 1/9, 8, negative 4, negative 1. So those are the two possible answers. Both are correct. Both will get full points. All right. By the way, we're going to talk more about planes very, very soon. And they're our preferred flat thing. So we're going to get to know them relatively well. All right. Well, thank you. Thank you for spending time with me. Thanks for doing the work and putting in the effort. I appreciate it. I know sometimes it's not easy. Some of these problems can be very challenging initially. But if you work on it, you'll see that they become easier and easier because you are getting better and better. Keep working. I believe in you. Thanks for joining me, and I hope I'll see you again. Bye.